Hello students. In the previous video we have seen the equilibrium constant expression for the general reaction. Let me remind you, the general reaction was, say, A mole of A reacted with B mole of B, which gives C mole of C and D mole of D. Small a, b, c, d are stoichiometric ratios and capital A, B, C, D are the reactants and products respectively. For this, we have written K value as molar concentration of C to the power C and molar concentration of D to the power D divided by molar concentration of A to the power A and molar concentration of B to the power B. Here, square bracket refers to molar concentration and its unit is mole per liter. Okay, we can say it as even per dm cube also. Liter can be even dm cube. As it deals with molar concentration, therefore we call it as C, Kc. Kc stands for equilibrium constant in terms of concentrations. That is molar concentration. Kc is this. Now, what we do is, if this entire reaction is gaseous reaction. If it is considered as gaseous reaction, then we will notice that there are some changes that can be brought into this. Let us see that. Now we are dealing with this reaction, assuming that all are gaseous substances. Look at this. I'll rewrite it. A mole of A gas reacts with B moles of B gas. This gives, upon reacting reversibly, C moles of C gas and D mole of D gas. Is it clear, students? Here, A and B are number of moles of gaseous reactants, and C and D are the number of moles of gaseous products. Remember this, students. These two remember it. A and B are the number of moles of gaseous reactants and C and D are the number of moles of gaseous products. See, students, here from ideal gas equation, we have PV is equal to nRT. Right, students? Okay. Here P is the pressure, V is the volume, N is the number of moles, and R is the gas constant, and T is the temperature in Kelvin scale. Then this can be written as, see here, P is equal to N by V R T. And this N by V is nothing but mole, number of mole per volume. Per volume can be, see here, 1 liter. So mole per liter. That means this can be written as concentration. Then what it will become? P is equal to, we can write it as CRT, where C is the concentration of the gas. Now we apply this equation for, see here, we apply this equation for converting concentration into pressure and pressure into concentration. And this is applicable for only gases. Liquids and solids do not come into this. Is it clear, students? That means here pressure of C, that means, say, we'll begin with A. Pressure of A, that means in this reaction mixture, pressure of A is given as, see here, pressure of A means C stands for concentration of A. That means molar concentration of A here. This C is nothing but square bracket. Square bracket is nothing but mole per liter, like this. So wherever C is there, we can replace it by square bracket. So pressure of A. Let's apply this for A. Pressure of A is concentration of A into RT. See, into RT. Similarly, pressure of B is equal to molar concentration of B into RT. Pressure of C is molar concentration of C into RT. And pressure of D is molar concentration of D into RT. Now let us use these values in this equation. Clear, students? Okay. Now what we do is we use this for CF. K in this way. What is this? This is K, and molar concentration of C means what is this? CRT. So this can be written as molar concentration of C into RT. One thing what you need to remember here is the power of this is the power of this entire thing. This entire thing. This entire thing. Like this. So C means here this power will be applicable for this entire thing, like that. Similarly, PA stands for, it will be like this. This will be like this, and this will be like this. So we can write it as raised to C into molar concentration of D RT whole raised to D divided by molar concentration of A RT then whole raised to A into molar concentration of C RT whole raised to C. Let's put this. Now we simplify this. Okay. Upon opening the bracket, what we notice? C to the power C RT whole raised to C. Clear? We have opened one of the bracket. Then D to the square bracket of D to the power D into RT whole raised to D divided by molar concentration of A to the power A into RT whole raised to A. Then if you remove this bracket, what happens? Into molar concentration of C raised to C into RT whole raised to C. Then we'll rearrange this equation. See here. Molar concentration of C to the power C into D to the power D into RT. See here. Bases are same, therefore power can be added. That means it will be C plus D. Divided by molar concentration of A to the power A and B to the power B into RT. See here, bases are same, therefore their power can be added. A plus B. 26 students. See here. What is this part now? This part is Kc. Isn't it? This is Kc. Therefore, this can be written as now, it can be written as K is equal to Kc. This part is Kc. Now, into, see here, here bases are same, therefore power can be added. Then what happens? RT raised to A plus B. Then, see here, it's not A plus B, it is C plus D. Then, if you take this to the numerator, what happens? The sign will change. That means minus A plus B. Well, as this expression deals with the pressures of reactants and products, therefore this K can be written as K, that is equilibrium constant, which deals with the pressure. That means Kp. Like this. This deals with the equilibrium constant of concentration of the substances. That is, therefore, it is Kc. Here, this is the equilibrium constant which deals with pressures of the substances. Therefore, it should be Kp. Kp is equal to Kc into Rp whole raised to. See, students, what is this? See here, C and D are the number of moles of gaseous products. This is number of moles of gaseous products, isn't it? And what is this? A and B. This is number of moles of gaseous reactants. This is number of moles of gaseous reactants. Well, this can be written as, this can be taken as, these two put together can be written as delta N. That means difference, it's not difference, it is the number of moles of gaseous products minus number of moles of gaseous reactants. Then we put one G here. This G indicates that this is applicable only for gaseous substances. Well, this indicates this. That means in place of CAD minus AB, what we can write is delta N G. Well, this expression we can get when equilibrium constant is dealing with substances which where their concentration instead of molar concentration if partial pressure or pressure is considered. That means this is the equilibrium constant in terms of partial pressure. Partial pressure stands for pressure of individual gas in the mixture of the gases. And this is the equilibrium constant in terms of molar concentration. Therefore, we can ask a question, derive the relation between Kp and Kc. Please, students, let me remind you. This is the situation when reactants are considered for their molar concentrations. This is the situation when the reactants and the products are considered for their pressures. Well, this deals with gaseous substances only. How it is, if one of them is, see, suppose this is not gas, either liquid or a solid. Then what happens? Liquid and solid do not exert any pressure. That means it will be taken, it will be eliminated. That will not be taken into the formula itself. So this will not be there. Is it clear, students? This is the derivation of Kp and Kc. Yesterday we have defined equilibrium constant in terms of Kf by Kb. That is ratio of rate constants of forward reaction to that of the backward reaction. And we have the same thing we have defined in terms of molar concentrations. That is molar concentrations of products to that of the reactants. Ratio to power equal to the stoichiometric ratios. Now we can define equilibrium constant in terms of pressure of the system also. So here pressure of the products divided by pressure of the reactants. Ratio to power equal to the stoichiometric ratios. That means equilibrium constant can be defined in how many ways? How many ways? This is first way, this is second way, and this is third way. That means equilibrium constant can be defined in terms of rate constants. That is, it is the ratio of rate constants of forward reaction to that of the backward reaction. Okay. Now in terms of molar concentrations. Okay. Equilibrium constant in terms of molar concentration is the ratio of the product of molar concentrations of the products to that of the reactants. Ratio to power equal to the stoichiometric ratios. Now in terms of K in terms of partial pressure. See here. Wherever this square bracket is there, square bracket can be replaced by P. That means we can write it as, see here, we can write it as Kp is equal to, see here, pressure of C to the power C into pressure of D to the power D divided by pressure of A to the power A and pressure of B to the power B. Okay. It means that equilibrium constant in terms of partial pressures can be defined as the ratio of product of partial pressures of the products to that of the reactants raised to the power equal to the stoichiometric ratios. That means equilibrium constant can be defined in three ways. One in terms of rate constant, another in terms of molar concentration, and last one in terms of partial pressures. This one says partial pressure means pressure of individual gas in the mixture of gases. This is the another article that will deal with this in due course of time. So partial pressure stands for pressure of that particular gas in the mixture of the gases that is present. Okay, students? Okay. Now we'll see the applications of this.